Okay, so let's take a look at a logarithmic function this way. Let's remind ourselves that the logarithmic function is the inverse of the exponential function. So since the exponential function would look like our output is, say, something like 2 to the input. So we input the exponent and we get out the result. So we input, say, a seemingly innocent number like, say, 5, and then our output is 2 to the 5, which is 32. So for an input that's fairly small, we get an output that's pretty large. And this sort of trend continues. By the time we're at x equals 8, we're at y equals 2 to the 8, which is, what is that? 256. 256. Okay, so we're inputting exponents and getting out results. With the inverse function, so we're going to take all of this and turn it around, so our x becomes y, our y becomes x, or vice versa, and we get this expression right here. This is the logarithmic function. So here, let's just get rid of the exponential function here. Okay, let's just get rid of the exponential function here. And we're left with the logarithmic function. Okay, so when I put in my x to the logarithmic function, I do something like, hey, I put in, say, an 8. And then I get out, well, I get out whatever exponent I need to raise an 8 or 2 to make an 8. So I get out a 3. So I put in the number and I get out the exponent. So if x equals 8, then I can see that y would have to be equal to 3 right here. Okay, so not really being satisfied with this way of writing the function, because our output is up here where we have to think really hard about it and blah blah blah, so we want to rewrite it so it's just y equals something. So it turns out that there's no simple way of rewriting this, so we had to create a whole new function, and it's called the logarithm. So y equals the log of x. This means y is the exponent that we have to write on 2 to make x. So again, we input our answer and we get out the exponent. So one way to deal with this is to instantly take this strange looking thing and rewrite it back in the original form here. So when you see something like this, here, let's go this direction instead. You might do something like base is 2, the exponent is what I'm trying to find, so that's y, and the answer that I'm trying to create with all that is 8. So we can solve something like this just by knowing that 2 times 2 times 2 is 8. So that means that 2 to the 3 is equal to 8. So y must be 3. Or I can think of it this way. 2 to the y equals, and then I'll try to write this as 2 to the something. Well, 8 is 2 times 2 times 2, and that means 2 to the 3. So 2 to the y is equal to 2 to the 3. That means y equals 3. Okay, let's try this one. So we're going to go base is 2. The exponent is what we're looking for. It's y. And the answer is 32. So I can do the same process. I need to write this 32 as a bunch of 2's. So that's 2 times 16. And that's 2 times 4 times 4. It's not a bunch of 2's yet. But wait, that's 2 times 2 times 2 for that 4. And then 2 times 2 for the next 4. So altogether, 2 to the 5. So 2 to the y equals 2 to the 5, y equals 5. Okay. Last one here. base is 2, the exponent that we're looking for, y, and the answer, 1/2. So, oh, the 2's are looking the same, but this one's on the top and that one's on the bottom. So how do I do that? Well, let's just remember that the alternate way of writing the reciprocal of 2 is 2 to the minus 1. So in order for 2 to the y to be equal to 2 to the minus 1, y must equal to minus 1.